My name is Singh Tomar, and this is my colleague Sandhya Vidyashankar. And we are here to present some of our work we have been doing at Clutterbot. Yeah, so agenda of the talk is we'll start by introduction, then we'll talk about the problem we are trying to solve at Clutterbot. Then we'll go over the solutions which we have tried and which you can also try, and some practical insights we have got while we were trying those approaches. So, introduction, who are we? We are Clutterbot, and we are trying to create tidy spaces for people with busy lives. The problem which we are trying to solve is the floor clutter problem, and we are placing ourselves somewhere in between the vacuum cleaners and the humanoids. So, as you can see in the images, floor clutter is quite diverse and complex. Like, it comes in all form factors, there is a lot of variations, and it depends a lot on the people who are living in the home. It depends on the geography where the home is. It also depends on the age group also, like if you have kids, if you don't have kids. So overall, it's like very diverse and complex problem. And to tackle it directly is like, you need a lot of information, you need sort of semantic understanding of the objects which are there, like you need to understand what belongs where, and it's sort of complex. So what we decided was that we'll start with a subset of this problem, which is the toy problem. And this is a general problem for people who have kids and both parents working. And it's a big of chore for them to actually clean the house every day, come back to home. And another reason for choosing this problem was that this problem is sort of constrained from the full floor clutter problem, but it still gives you the same flavor. Like it has toys comes in all shapes and sizes, they come in all form factors, they come in all sort of materials. So then how do you design something which can pick up something which has so much of variations? Like you can think of any of these robots. Like you have a wheeled robot which has an arm on top of it, or you can have legged robots which have arm on top of that, and you can try to pick up stuff with that. But do you really think, like if you look at the image on the very left here, do you think it's feasible, or it's economical to actually start picking each Lego with an arm? I don't think that's timely economical. And another factor which we need to consider here is that the robot needs to work in home. Like it needs to work alongside people, it needs to work alongside kids, pets. It needs to have a physical appeal to itself. Like you should look at the robot and feel like, yeah, I can make this robot a part of my home. Which brings us to the platform. And the platform we build is Rovi. This robot is a differential drive robot. It has front and back facing cameras. It has in total 8 actuators. And this is a video when we took the robot in Roscon, Singapore. So as you can see, I feel the robot is very cute. I don't know, like, how do you feel? So this is sort of the hardware overview of the robot. In total, it has 8 actuators, 2 in arm, 2 in palms, 2 in scoops. So the way it works is basically the software is controlled by a complex behavior tree, but roughly you can understand it like this. The mobile app will talk to the top level behavior. Behavior will talk to perception system, which will tell the robot what is an object of interest. In this case, the object of interest is a toy. It will take that information and pass it over to navigation system, which will take the robot to that area where the object of interest lies. And then the manipulation system will basically pick up the stuff and put it away. In rest of this talk, we'll basically focus on this manipulation system, and we'll see what different approaches one can take to come up with such a manipulation system. Which brings us to our first solution, which is direct position-based control. For any manipulation-related work, this is a simple approach you can take. What you can do is, if you have actuators, you can define what are the target position they can be in at any given state. And if you define all of those states, you can come up with a sequence for any task. Like if you want to do the sweep, you can come up with a sequence of target position for each of those actuators, and you can command those actuators to go to those positions, and you will be able to do that sequence. As you can see, the motions are very discrete, and you can see like every actuator is going to a target position. Yeah, and this is how it looks when you actually put the whole system into full autonomous mode. And the system has its pros and cons. Like it's easy to implement. You can create new sequences very easily. It avoids self-collision, obviously because we are only moving one actuator at a time, but it's very slow. And it cannot handle a lot of edge cases because it will always try to achieve the same position even though if there is something. It has no understanding of environment. Which brings us to our second solution. So what do you do when you need understanding of the environment? Like you need to understand the 3D aspects of the environment. So you start with a 3D sensor which can provide you depth information, and you pass it into the system. Another thing which we wanted was that we wanted multiple actuators to move at the same time. So you can get all of these things if you move towards MoveIt. MoveIt is sort of a planning library which is again provided by Ross. You can pass in your 3D information to the system, and then you have basically a better understanding of your system and how MoveIt works with any of the system. You can get a high level goal, you take that goal, and manipulation system can talk to MoveIt. That goal will then be divided into trajectory of multiple actuators, and then you can send that trajectory to low level and to hardware for further execution. And you can see this is how it can look like if you execute trajectories. The difference here from the previous videos, you can see that the multiple actuators are moving at the same time, and the motions are a little bit, like they are smoother than the previous one. But when you start working with MoveIt, there are multiple things which you need to consider. And there are issues which come up when you start working with MoveIt. And these are some of the main things which we figured, like we found out when we were working with MoveIt. And I'll talk about in more detail in some of these, but it needs a lot of tuning. And even though your environment is static, let's say, if you give repeated planning requests, there's a very good tendency that you receive different plans each time, even though the environment is static. So what is the issue with this multiple kinematic chain system? So you can think of kinematic chains like if I'm a robot and this arm is an arm, a robotic arm. So all of these joints forms this actuator. This forms a kinematic chain. And MoveIt inherently is designed to solve kinematic chains, the inverse kinematics for single chain system. But our robot has 3 chains, like 2 for palms and 1 for scoop. Inherently, MoveIt doesn't support that. Like you cannot, there is no direct way. There are ways to do it, but there is no direct way to solve inverse kinematic for such a system. So how we use MoveIt in that case was we used it just a planner. Like MoveIt can still solve forward kinematics for you. If you can come up with an algorithm which can give you target angles for your actuators, MoveIt can still give you self-collision-free trajectories. What else you can do is, if you further want, since we have depth information, we can process that depth information and pass it to MoveIt system, and that can give MoveIt the understanding of environment, like things which you can consider obstacles and things which are not obstacles with which you want to collide. So that's one way you can use MoveIt if that fits your problem statement. Second thing was high compute usage and redundant motions. As I talked earlier, that MoveIt, by default, the fast planners in MoveIt, they are sampling based. And sampling-based planners have this tendency to have redundant motions in them. If you want optimized motions, then you can either constrain those samplers, or either you can use other planners which are optimization-based, but they take a lot of time, and you cannot use that in online planning. So what you can do is, you can use the trajectory caching feature in MoveIt. And you can come up with a script which can generate, let's say, random goals for you, and you can run it offline and generate smooth trajectories, because time is not an issue for you right now. You can generate optimized trajectories, save them into the database, and when you receive a new goal, what you can do is you can query that database and ask if, okay, do I have a trajectory which takes me from this position to the target position I want to go? If you get the trajectory, you just execute it. But that doesn't include any environment obstacles. So if you want your fetch trajectory to be validated again, what you can do is you can pass it to planning scene monitor. It can validate the trajectory for you if it is still valid with the current environment. And depending on the environment, it can fail or it can pass. If it passes, good, you can just execute it. But it fails, then you fall back to the online planning. You plan it again and then execute it. Even though MoveIt solves a lot of our problem from the previous system, but there are things we want from our system which MoveIt doesn't give us. Like it doesn't give us any sort of semantic understanding of the scene. It doesn't give us any textural help. Like if we cannot do stuff if something is soft or something is hard. We have a lot of data, but we cannot use that data in any sort with MoveIt. So that brings us to our next solution, and my colleague will take over here.
Okay, thank you, Robin, and hello, everybody. I'm Sandhya, and I will be talking about our third solution, which, as you may have guessed from the cats, is a learning-based solution. So let me just pick up where Robin left off and talk about the limitations with our first 2 approaches. So our initial direct position approach had the issue of being slow. It couldn't really avoid obstacles or handle edge cases very well. Meanwhile, our MoveIt-based system, while it was excellent, for our specific use case, the lack of textual and semantic understanding was not the best. Also, in addition to that, the biggest thing was that this system could not really learn from experience or adapt to new scenarios. Yep, I said learning. So this brings me to our next solution, an imitation learning-based solution. Most of you are already familiar with imitation learning, but why we went forward with it was mainly because of its simple implementation, the fact that it's really reactive to environmental changes, and also gives us very smooth and intuitive motion. Our robot is a very customer, consumer-facing robot. So we want somebody to look at the robot, move, and think, oh yeah, that's how I would have done that. So how exactly did we go about implementing this solution on Rovi? So the first step was, like most things, research and understanding. So when it comes to imitation learning, we have a lot of different algorithms, and a lot of people have already spoken about them in great detail. I won't be talking a lot about this, but basically we have behavior cloning. Behavior cloning is the simplest form of imitation learning, where an agent learns how to mimic an expert 1:1, basically. We also have VLAs, specifically small VLA. Everybody knows what a VLA is. We've had a lot of talks on this. But small VLA is a very lightweight version of a VLA, consisting of only about 450 million parameters. And this is basically offered by LeRobot. LeRobot has a lot of open source resources for implementing end-to-end imitation learning-based solutions. And it's also integrated with the cloud. It's a great place to get started if you're looking to get into imitation learning. And the good thing is that they also offer these open source arms. Again, highly recommend for all of you, if you check out the QR code if you are a student looking to get into imitation learning. But these arms are completely open source and are directly compatible with the LeRobot library to start. So that's exactly where we started our journey with this hackathon that we attended in Bangalore, conducted by LeRobot, where we train the robots to pick up anything that's not Legos. So we can teleoperate it with the black arm, as you can see Robin doing in the video, and the white arm will follow, allowing us to basically gather very clean data. After this, we then proceeded to do an ablation study. So in general, most learning-based algorithms have a lot of knobs that you can tune. And the best way to kind of get into it is to immediately get your hands dirty and start actually working with an ablation study, working with the robots. So we focused on a smaller subset of our problem, basically just to understand it better, where we wanted to pick these Lego blocks and place them in a tray. Something I'd like to draw your attention to here is that we use 2 cameras. The reason we use 2 cameras is because a single camera view, it does not give these algorithms a lot of depth data. So in general, from a lot of discussions online, we learned that having multiple cameras allows the algorithm to basically infer depth data. In addition to this, we varied a lot of parameters while we were training. We varied the number of cameras, the training steps, the data set size. All of these are straightforward, but specifically something that we varied is the chunk size. So if you guys remember from the talks yesterday, ACT or action chunking is an example of a chunking-based approach. So most behavior cloning just predicts one action for every observation, while these algorithms predict a sequence of actions. With varying the chunk size, we're basically varying how far in the future the model is going to predict actions. This will result in the robot moving slower or faster, maybe a little jerkier, and also basically tuning its reactivity to the environment. And from this ablation study, we kind of understood how this affects things, allowing us to go ahead and implement stuff on our robot. But there was still one thing that we had to figure out, an intuitive teleoperation system. If you remember Rovi, it has 6 actuators that are involved directly in manipulation, not counting the wheels. 2 arms, 2 palms, and 2 actuators in the plow. Technically, a PlayStation controller or any controller has enough buttons, but it doesn't feel very natural to control something like this using that. So we went ahead and built our own leader-follower setup. So the basic configuration is here. We didn't have any control over the plow, but we could just manually move like detached arms and palms. And this was all connected to a Jetson and was talking to the robot. We've recently developed a more advanced version of this. That's a joystick-based control that's just much easier for us to use to collect clean data. Something that you must know about imitation learning in general is the quality of the data that you collect is very important. So you need clean data because the model is assuming that the expert knows best all the time. So if the expert gives it bad data, the model is going to learn the noise. And you're going to see noisy behavior from the robot. Then coming to the third step, where we integrated this system with our ROS-based robot. So the first step was, so for our LeRobot system, a basic LeRobot system just directly reads camera and head-off data as well as joint angle data, feeds it directly into the model, just reading it with USB connections to the cameras and whatnot. But we specifically needed to use ROS2 because our robot is a ROS-based robot. So we actually integrated this OpenPR for these ROS2 camera plugins, as well as adding in a ROS2 subscribers, just a simple middle layer that would allow us to make a custom robot, to customize our robot to work with this existing setup. After this, we finally get to the fun part, where we collect data and deploy everything on the robot. So first off is the networking. If you remember, we have a camera and a headstuff that is very heavy image data. If we're doing everything over Wi-Fi, we're going to have a lot of latency. And with how important clean motion is, having latency with the teleop means that we're not going to get great motion. So we used a LAN cable to connect the robot to our laptop where we were recording all of the data. We also used Wi-Fi then to connect with the teleoperation setup. So this would basically make it much less laggy and much smoother during operation. Then when it came to actually collecting the data set, so this is a screenshot from the Lee robot actually, like from the data set that we have. So here you can see 3 cameras. The one on the far left is the raw camera data. The one in the middle is segmented image data. And on the far right, you see headstuff data, high time of flight, point cloud data, except it's done as a depth image. If you remember what I said earlier, this is basically to give the model a lot more understanding of the depth of the relations in the scene, so it can get better inferences based on where objects are in the environment. In the bottom, you can see all of the joint data, which was also being recorded and inferred. So here we can see that we have 4, we're just controlling the palms and the arms here. And when we were actually recording the data, we recorded 450 episodes of teleoperation data. That was not easy. If you don't believe me, ask my colleagues. And so with this, the data had to be very clean. So we were very careful while recording it. And for all of you who are getting into imitation learning, one very important tip is to be increasing the variability very slowly. Like let's say you're doing something like this. If we give it every toy in a house, it's not going to perform great. That's too much variability with, even though we have 450 episodes, still too little data. So we use just permutations and combinations of about 15 toys, some of which you can see on screen, and teleoperated it in this fixed position. Basically, now one piece of variability we've reduced again is the types of floors, because in real households, we'll have a lot of different floorings. And during this data collection, we made sure that anytime the two actuators touch, that episode is junked. We're not using it. Also did one round of manually checking as much as we could for the size of the data set to just make sure that everything was actually exhibiting the kind of behavior we would want the robot to exhibit. This brings me to the results. So the first video on the far left, you can see it picking up the kind of toys that we've already trained it on. One really interesting thing here is when it's trying to pick up this toy shoe, it gets stuck under the arm and it actually recovers very well. This was one of the issues with our earlier approaches, if you remember. Then in the second set, actually this pink couch is a bigger toy than anything that we've trained it on. And left to itself, the model could not recognize it at all. It did not react. So we've added toys that we've already seen on top of this, and then we see it react. But it still does recover pretty well, I would say, considering that this is a completely new type of thing to pick up. Finally, the last one is one of the most interesting things because it's never seen these two toys before, but probably because we're giving it segmented data, we're giving it bounding boxes, it's able to detect and sweep and pick these up. So this brings me to the conclusion of our presentation. As you guys all know, and as you've seen, a VLA is a great solution. It has a lot of advantages, but it is not a silver bullet, and it's not all rainbows and sunshine. I think it's important that we know that the type of solution that we're using has to be very specifically tailored to our specific system. Like in our case, for example, the VLA showed like good recovery, but it did not give very deterministic results that we might get from a more classical approach. In addition to this, data collection, like I keep saying, data collection is the biggest thing. We had resources to actually build an intuitive teleoperation system. This is not the simplest way to go about it. For buying multiple robots, that's going to cost more money. There needs to be time and effort put into developing proper teleop. So this is something that is very important, and getting good quality data is very, very time consuming. Finally, these models need a lot of compute. All of the inferences you saw before, those inferences were run on my laptop. My laptop with a powerful GPU. So we were actually running it on the Jetson that we have on the robot or any other edge compute. that's going to be very different. That's going to take a lot more effort. But I think it's also important to note that we need to remember that using a ROS-based solution opens us up. ROS is not a limitation. We have so many open source resources, and it's completely up to us to combine them and to come up and innovate with new things. So we really hope that this talk has helped you all on your journey with imitation learning and given you some insights from what we've done and what we've learned. It's been great talking to you all, and thank you. Please do check out Clutterbot and our profiles on LinkedIn.